Hello dear students, this is grade 12 mathematics lesson on unit 3 introduction to differential calculus. So today we focus on derivatives of a function at a point. So after revising this lesson, you are expected to find equation of tangent line to the graph at a point and identify differentiability of a function at a point and on interval. So let's continue to lesson. Let's see this definition. The derivative of a function. The derivative of f at a point A is the limit of quotient difference if it exists. This means if we have a function like this, if we are asked the derivative of this function at A, so this assume we said it is f of x. We need to find 2 points. Let's take a point here, A plus h. So between these two, try to find the slope of this expression. When you find the slope, this point is A plus h comma, this point it is A plus h comma f of a plus h. It is f of a plus h. And this point is a comma, this point is a comma f of a. So to find the slope, simply take the difference of y to the difference of x. So the derivative of this expression at this point is given by the limit of f of a plus h minus f of a over h, where h goes to 0. So the derivative of this function at point A, simply you take the slope, simply it is f of a plus h minus f of a divided by the difference of the two, a plus h minus h. So you get this result. And when h is very close to 0, when h is close to 0, these two numbers are closer. So in that case, you will find the derivative at that point, the derivative of the function at that point. So it's defined in this form. F derivative of a, this is equal to this, f of a plus h minus f of a over h, where h goes to 0. Or you can write in this form. The derivative of a function at a is given by, in this form, the limit of f of x minus f of a over x minus a, where x approaches to a. This is how the formula to evaluate the derivative of a given function at a point. And the derivative of a function at a point means it is the slope of tangent line at that point. This means, look, if we have this graph, the derivative of This function at this point means it is the slope of this tangent line. That means let's take this to be a and this function to be f. So the derivative of the function at point A, this is equal to this, the slope of the tangent line at that point. So we can write the equation of tangent line at that point using this equation, using this equation, y minus f of a, this equal to f derivative of a times x minus a. This means, look, we have the slope here. The slope is this m, or it's f derivative of a. To write the equation of this tangent line, we have this point. This point is this a comma f of a. Let me write it here. It is a comma f of a. So we have this one, and we have the slope, So to write the equation of this tangent line, it is a point slope form. It's a point slope form. So y minus f of a, this equal to m times, this is the slope, f derivative is the slope. So m times, it is x minus a. So this is a formula to write the equation of tangent line at a point for a given graph. So now let's see example for this concept. Look, this one. This question is given. Find the equation of a tangent line to the graph of f of x is equal to x squared at x is equal to 5. To write the tangent line equation, first I need the slope. The slope is simply, it's the derivative of that function at that point. So the slope of the line is simply the derivative of the function at 5, f derivative of 5. So to find the derivative, you can use this formula just we stated earlier. The derivative of the function at 5 is simply the limit of f of x minus f of 5 over x minus 5, where x approaches to 5. So this equal to f of x is given, it is x squared minus f of 5, when you put 5 here, f of 5, it is 5 squared, 25 over x minus 5. So when you factorize this to find or to evaluate the limit of this one, x squared minus 25 means it is x squared minus 25 means it is x minus 5 times x plus 5 divided by x minus 5. So these two cancels out, only x plus 5 is remaining. Therefore, the limit of x plus 5 when x approaches to 5 is 5 plus 5, it is 10. This 10 is the slope of a tangent line. This 10 is the slope of tangent line. So once we have found the slope, we can write the equation using the formula. It is y minus f of a. Our a is in this case 5. Y minus f of a, or f of 5, is equal to the slope, it is f derivative of 5, times x minus 5. So putting the result is y minus f of 5 is this 25. F of 5, when you put 5 here, 5 squared is 25. This is equal to the derivative of the function at 5 is this given, or we calculated here, it is 10 times x minus 5. Therefore, when you simplify this, you get y is equal to 10x minus 5. So this is the tangent line equation for this graph at x is equal to 5. Now let's see another example. Here say find the equation of tangent line to the graph of f of x is equal to 1 over the square root of x at x is equal to 4. So to write the equation of tangent line, we need first the slope at 4. The slope at 4 means f derivative of 4. So let's find this. So f derivative of 4, this means it is the limit of f of x minus f of 4 over x minus 4 when x approaches to 4. So our f of x, it is 1 over x minus f of 4. When you put 4 in the function, it is 1 over the square root of 4, it's 1 over 2. So 1 over square root of x minus 1 over 2 divided by x minus 4. So this is equal to the limit x approaches to 4. When you simplify this, first let me write this 1 over x minus 4 here. And this result will be this 2 minus the square root of x over the product of 2 root x. And to find the limit, we need to rationalize the numerator. To rationalize the numerator, multiply by 2 plus the square root of x, 2 plus by 2 plus square root of x. So when you simplify this result, this product will be it is 4 minus x. When you multiply this, you get 4 minus x. And 4 minus x cancels x minus 4. When you take the ratio, it is negative 1. It's negative 1 over the remaining part is this 2. It is 2 root x times 2 plus the square root of x. When you put 4 in this expression, you get negative 1 over 16. Therefore, the slope of the tangent line at 4, or f derivative 4, is this negative 1 over 16. Now, once we have found the slope, we can write the equation using this formula. So y minus f of a, our f of a is 4 here, y minus f of 4, this equal to the slope, it is f derivative 4 times x minus 4. So putting the numbers here, y minus f of 4 is this, you put 4 in the function, 1 over square root of x, 1 over 4, square root of 4, it's 1 over 2. This equal to the derivative at 4, that's the slope. We have found it is negative 1 over 16, put negative 1 over 16. So times x minus 4, when you simplify it, you get y is equal to negative 1 over 16x plus 3 over 4. So this is the tangent line equation for the graph of f of x equal to 1 over square root of x at x equal to 4. Now let's see this example. Let f of x is x cubed minus 3x. You are asked to find the values of x at which the slope of this tangent line to the graph of f of x is 0. So the slope is 0 means the derivative of this expression is 0. So find that value of x, or in other words, it means find the value of x at which the derivative of this expression is 0. So let's find it. So simply the derivative is 0. Let's find the value of x. So the expression here, it is f of x equals to x cubed minus 3x. Its derivative is, put 3 in front and subtract 1 from the exponent. So this equal to 3x squared minus the derivative of this one, it is 3. This is equal to 0. So when you just evaluate this one, you put 3 there and divide by 3, you get x squared is equal to 1. Therefore, from this, x it is plus or minus 1. Therefore, at x equals to 1 and negative 1, the slope of tangent line for this graph is, it is 0. This means. Okay, now let's see another part, differentiation of a function at a point. Differentiation a function at a point. Now, let f be a continuous function at x naught. If the limit of f of x minus f of x naught over x minus x naught, where x approaches to x naught, is equal to infinity, or the limit of f of x minus f of x naught when x approaches to x naught is equal to negative infinity, then the vertical line x equal to x naught is a tangent line to the graph at x naught comma f of x naught. So let's see example for this concept. Here, find the equation of tangent line to the graph of f of x is equal to x the power of 1 over 3 at x is equal to 0. Now, to find the tangent line equation, we need the slope. So the slope is evaluated using this expression, quotient difference. That's the limit of f of x minus f of x naught over x minus x naught, where x approaches to x naught. So this implies the slope is equal to our f of x is this x the power of 1 over 3 minus our f of x naught, means you put 0 in the function, 0 is the power of 1 over 3, it is 0. So over x minus x naught, our x is a variable, minus our x naught is 0, so x minus 0. When you simplify this, you get this result. When you simplify this, it will be this x the power of, you take the difference of their exponent, 1 over 3 minus 1, it is negative 2 over 3. So this will be this 1 over the cube root of x squared. So when x approaches to 0, this number will be very small. 1 over very small number is goes to infinity. Therefore, the limit of this expression will be this infinity. Since the limit or the slope is infinity, the tangent line at this point is a vertical line. So the equation of tangent line will be the vertical line x is equal to 0. So it will be the vertical line x equal to 0 is it is tangent to the graph at 0, 0. Okay, now let's see another part. Let's see definition. If I is an open interval, then we say that a function f is differentiable on I if f is differentiable at each point on I. Okay, and if I is a closed interval, this, then we say that f is differentiable on this closed interval AB if and only if this function is differentiable on open interval AB and it is differentiable from the right side of A and differentiable from the left side of B, which means that the limit of f of x minus f of A when x approaches A from the right side must exist, not on this one. The limit of f of x minus f of b over x minus b when x approaches to b from the left also exists. In that case, the function is differentiable on a closed interval AB. By the way, a function is differentiable on this interval means it doesn't mean that the function is differentiable at A. This means it is the function is differentiable from the right side of A. In addition to that, a function is differentiable on the left side of B. Okay, so now let's see example for this. We have these questions. Try to find the differentiability interval for this function. Here f of x is given, another function is given. Let's see this turn by turn. Now let's see this one. F of x is equal to x if x greater than 1 and 2 minus x squared if x is less than or equal to 1. Here we are asked to determine the differentiability interval for this function. So let's try to find the derivative of this function. The derivative of this function for x greater than, let's leave 1 first. For x greater than 1, this function is given, its derivative of x is 1. For x less than 1, let's exclude 1 here. For x less than 1, the derivative of this function is minus 2x. So we need to check the derivative of this function at x is equals to 1. To check that, we have to check the right side and the left side derivative at 1. The derivative of this function from the right side of 1 is this one, it is 1. So f derivative from the right, f derivative of x from the right side, from the right side of 1, from the right side, let's write like this, from the right side of 1 is this part, its derivative it is from the right side is 1. From the left side, if you take from the left side, you take this expression, so its derivative it is minus 2x, minus 2x times 1 is minus 2. From the left side of 1, its derivative is minus 2. From the right side of 1, its derivative it is 1. Since they are not equal, the derivative of this function at x is equal to 1 does not exist. So to write the differentiability interval, it is differentiable from 1 up to infinity. From the right side of 1 is also its derivative 1. So it is differentiable from negative infinity up to 1. That means from the left side of 1. From the left side of 1, its derivative is minus 2x. For x less than 1, its differentiable, it is negative 2x. So from negative infinity up to 1, it is differentiable. Not only this 1. From the left side of 1 is also its derivative, this part. So it's differentiable from the left of 1. So 1 is closed. And for x greater than 1, its derivative is 1. So it is differentiable from 1 up to infinity. To check, to close this one, let's check whether it is differentiable from right side or not. From the right side of 1, its derivative is this one. Therefore, it's differentiable from the right side of 1. So I can close this one. So the differentiability interval of this function is this from negative infinity up to 1 closed, and from 1 up to infinity, but it is not differentiable at 1. It's not differentiable at 1. Now let's see this one. F of x is equal to the square root of x minus 2. Let's just try to find the derivative of this expression. The derivative of this expression f of x is equal to square root of x minus 1. We can use this formula in which if we have the function of square root of x, you can derive the formula anyways. The derivative of the square root of x this equal to this 1 over 2 root 6. Similarly, you can derive the derivative of this expression to be it is 1 over 2 the square root of x minus 2. Its derivative it is 1 over 2 square root of x minus 2. So to find the interval in which this function is differentiable, simply you take the domain of this expression. The domain of this expression is simply x minus 2 must be greater than 2. So x minus 2 greater than 0, it must be greater than 0. This value x minus 2 must be greater than 0. So this is x is greater than 2. It can't be 0 because it is this number is on the denominator. Therefore, this function is differentiable from 2 up to infinity, or it's differentiable on x greater than 2. This is the interval of differentiability of this function. Now, let's see. So, hence f(x) is differentiable on 2 up to infinity. Now, let's see this function f of x is equal to absolute value of x plus x minus 1. We are asked to find the interval in which this function is differentiable. So to do this, first I need to write this in a piecewise function form. So for that, let's try to write this in a sign chart form. Look, x is equal to 0 and the boundary numbers for this x equals 0 and x equal to 1. So here we have absolute value of x, and the other one is this absolute value of x minus 1. Therefore, I hope you remember the definition of absolute value. Absolute value of x is itself for positive number, negative x for negative numbers. So when you put negative numbers here, so for this one is negative number, its absolute value must be negative. So for this interval, absolute value of x is negative x, which means absolute value of x is equal to x for x greater than or equal to 0 minus x for x less than 0. So for x less than 0, this one is minus x. And it will be for x greater than 0, it is x. Now let's take this one, absolute value of x minus 1. For x, absolute value of x minus 1, if you put 1, it is 0. For number less than 1, this will be negative. So its value is this, negative of x minus 1. This will be also negative of x minus 1. For x greater than 1, its absolute value is itself. So it is x minus 1. So combining this, you will have this one. F of x is equal to, for x greater than or equal to 1, for x greater than or equal to 1, the sum of the two, it is 2x minus 1. For x greater than or equal to, the function will be, this expression will be this, 2x minus 1. And between these two numbers, the sum of these two, it is x plus negative x plus 1, it becomes what? 1. So between this interval, it is 1. And for less than 0, for x less than 0, you add these two. When you add these two, it becomes negative x. This becomes plus 1. So minus 2x plus 1. So this function is the same as this one. So we can simply find now this derivative interval of differentiability. So let's find its derivative. The derivative of this function for this part, for x greater than 1, not including 1, for that case, its derivative of this expression is 2 for x greater than 1. And between 0 and 1, since the function is constant function, its derivative is 0. So it's 0 for this number without including the border, without including 0 and 1. For this interval, its derivative it is 0. And for x less than 0, the derivative of this expression is this, negative 2. The derivative of minus 2x plus 1 is this, negative 2. Okay, so after this, we need to check whether it is differentiable at x equal to 1 and at x equal to the border. Check that, look. Check at 1, the right side derivative is this 2. The left side derivative at 1 is this 0. They are not equal. It's not differentiable at 1, since the right side and the left side derivative of the function at 1 is not equal. Because of this, it's not differentiable at x equals to 1. And let's check at x equals to 0. The left side derivative of the function at x is, from the left side of 0, its derivative it is negative 2. And from the right of 0, it is derivative is 0. Since these two are not equal, this function is not differentiable at x equal to 0. So I can now I can write the interval of differentiability of this function. So here this function it is differentiable for x less than 0 from negative infinity up to 0. It is differentiable also from the left side of 0. So it is differentiable on negative infinity up to 0, including 0, the interval negative infinity up to closed interval 0. Okay, now next to this, from 0 to 1, it's differentiable. From the right side of 0, it's differentiable, this one. From the left side of 1, it's differentiable. So it is differentiable on closed interval 0 to 1. And from 1 up to infinity, it is differentiable. From right side of 1 itself, this one is differentiable. So the differentiability interval for this function is this one. Okay, now let's summarize the key pointers that we have seen today. The first one is the derivative of a function at a point A is given by f derivative of A is equal to the limit of f of A plus h minus f of A over h, where h goes to 0. And the tangent line equation for the graph of f of x at A, this is given by y minus f of A is equal to the slope f derivative of A times x minus A. And the other part, if I is a closed interval AB with A less than B, then we say that f is differentiable on I if f is differentiable on open interval AB and the right side limit, or it is differentiable from the right side of A and differentiable from the left side of B, which means that the limit of f of x minus f of A when over x minus A, where x approaches to A from the right, must exist, not only this one. The limit of f of x minus f of B over x minus B, where B approach from the left, must exist. If these two exists, it is differentiable on a closed interval AB. So this is all about today's lesson. So I'll give you exercise for you to try. So please try these questions. I gave you 4 questions here. So I'll give you 1 minute to write this question. This is all about today's lesson. I'll see you on next lecture. Until then, goodbye.